All right. Wow, okay, so the announcements are the same. Remember, the labs will start on Monday. Let's quiet down, please. We have the extra credit problems going, assignments going on. So I've gotten a few emails from people that have had bits of problems along the way, but I'm hoping that they've gotten sorted out. All right, so everybody's been able to get into those assignments that's tried? Okay. All right, remember we'll try to have an iClicker tomorrow, if I can remember how to do that. On yesterday, we started into the discussion on mass spectrometry. We first gave a little discussion over the different structure determination techniques, and then we focused on mass spectrometry. So we looked at the process, right? The fact that when we do mass spectrometry, we have to take a molecule, we bombard it with an electron, it excites the molecule, and it ejects an electron. And so we generate a radical cation. So it's a species that has both a radical and a cation. That species we can analyze directly, or it can fragment into smaller pieces. When we run the spectrum, we analyze only the cations. Okay? And so we can look at a mass spectrum. We get a peak for the molecular ion, usually, and then peaks for different fragments. Okay? From that information, we started looking at how we might get information about the molecular formula. So we went through kind of a stepwise process where we would take that mass. So what we did was we took the mass and we first divided it by 12, because that's just the maximum number of carbons we could fit into that mass. Usually we got some formula with a number of carbons, and whatever the remainder is hydrogens. But most often there we got a formula that had too few hydrogens for the number of carbons. Okay, so then after we did that, we usually subtract one carbon and we trade that in for 12 hydrogens. We're just getting into the range of possible formulas. If we think there might be oxygen, then what we can do is minus CH4 and add an oxygen. We can do that again if we need to. Okay? So we're going to look at some more things about molecular formula. After that, we're going to say, once we have a formula, what information can we gather from that? One is that we can calculate the number of unsaturations. We'll talk about that. And then we'll start to talk about the actual fragmentation, how the molecule cleaves apart. Once we've done that, we'll look at some examples. Okay? And if we're fast enough, we'll even look at start introduction to IR. All right, any questions? All right. Okay, so far we've looked at spectra that had carbon, hydrogen, and maybe oxygen. All right, so let's look at these two spectra here. Now the scales are a little bit off. This one has a molecular ion right here at 72. All right, and this other one over here has a molecular ion. I'm going to just tell you that these are the molecular ions. This one is at 73. All right, so let's just start out. I'll just show you the structures for these compounds, and what we want to do is pick out something about them. So this top structure is, I think, just the one that we saw before. This is just for pentane. Okay, and this bottom one is this amine right here. Okay? And so the thing that I want to point out is that in this structure up here, we have a molecular ion with an even mass. All right? And when we have a molecular ion with a nitrogen, or an odd number of nitrogens, we have only one, we notice that the molecular ion has an odd mass. Okay? And this gives us, or comes up with what's called the nitrogen rule. Okay? And I can fit this in here or something. The nitrogen rule basically says if the molecular ion has an odd number of nitrogens, it will be odd. It will have an odd number. Okay, so one nitrogen, we're going to have an odd mass. If, alternatively, we have an even number of nitrogens, including 0 or 2, then the molecular ion will have an even mass. All right? So, the trick here is that we said before that the highest mass, well, the molecular ion has to be the highest mass ion in the spectrum. Okay? But we also talked about the possibility that the molecular ion would not show up at all if it cleaves too readily. What we see here, so we start at 72, that cleaves, loses a methyl, and we get 57. Okay, so notice that we're going from an even mass molecular ion to an odd mass fragment. Okay, and that's the usual trend. If we go further down, the biggest ions are 43 here. Again, we're going from an even mass ion to an odd mass fragment ion. And this is going to be the most common situation. Okay, notice in the spectrum of the amine, we go from an odd mass molecular ion to 30. This has an even mass fragment ion. Okay, so if our cleavage, our fragmentation, cleaves one bond, and we're not going to really go through we're not going to go through mechanisms of how these cleave, but the general things are, the most common situations are where we'll start out with an even mass if there's 0 nitrogens, and we'll get odd massed fragments. Okay, and it's just switched if we have an odd number of nitrogens. Okay, this is the nitrogen rule. So this can give us, if we have some indication that we are starting with a molecular ion with an odd mass, that it contains nitrogen. Okay? So it can be a little tricky though, but this is one additional piece of information. Another thing that we can see is if we have halogens in the molecule, particularly chlorine and bromine. All right, these two spectra are kind of related in that they're both structures with a halogen attached to a benzene ring. So the top one is chlorobenzene, the bottom one is bromobenzene. Okay, and so of course, and the scales are different. This one here looks like this is at 112, 112 here, and over here this is at 156. But notice that there's 2 peaks in both of them. So this is 156 and 158. The one for chlorine has this big one at 112, and then this smaller one that's still pretty big at 114. Okay, so in these two cases, the molecular ion has a pair of ions. All right, so any idea what that might come from? It's similar to the reason that we saw that M+1 peak. All right? And that's, the reason is because both chlorine and bromine have very prominent isotopes. They have two different isotopes. Okay, so for chlorine, chlorine can come in chlorine 35 and chlorine 37. Right? So what we're actually seeing is one molecule with chlorine 35 and another molecule of the same thing with 37. Okay, we can see those separately, and because the ratio, the natural abundance ratio of chlorine, 35 to 37, and I'll show you a table of this, is roughly 3 to 1. So every time we have a chlorine in a molecule, we'll see a pair of peaks. So this would be the M and the M+2 in a 3 to 1 ratio. Okay, so if you see two ions apart like that for a molecular ion, or even a fragment ion that are in a 3 to 1 ratio, two mass units apart, you'll go, aha, there's chlorine in the molecule. Even easier to pick out is this M and M+2 of almost equal amounts for bromine, because bromine has bromine 79 and bromine 81 in almost 1 to 1 ratio. Okay, so these are going to be, bromine is especially easy to pick out. Notice that only in these two cases, only the molecular ion has the chlorine or bromine. Once we look at any of the fragment ions, that halogens come off. Okay? All right, so those are the easiest to pick out with different isotopes. And let's look at the different masses of some of these elements and what their isotopes are. So for hydrogen, there are some different isotopes. So here's the mass on the periodic table, and that's made up of two different isotopes. We have the proton and the deuteron, so hydrogen and deuterium. And those are in a 99.99% to 0.01 ratio. So notice that the periodic table mass over here doesn't correspond to either of those isotopes, but what that represents is a weighted average of those two masses. Okay? If we look at carbon, the mass of carbon, if we look at the, do we have one in here? No. A periodic table says 12.011, but that comes from a 98.9 to 1.1% ratio of carbon 12, which has a mass of exactly 12.000, to carbon 13, which is 13.003. Okay, so, well, here, let's continue on. Oxygen has two isotopes, 16 and 18 are their most abundant. And here's the two we were just talking about. Here's chlorine 35, has a mass of 34.9688, and 37, 36.9659 in an almost 3 to 1 ratio. And so the mass that we see on the periodic table is a weighted average of those. So the point here partly is that when we do mass spectrometry and we want to add up the masses to come up with a a molecular mass, we cannot use the periodic table because that's a weighted average, okay? Do not use periodic table for masses. Because in mass spectrometry, we can see the difference between those isotopes. We can't mix together the masses. All right, so here's the 3-to-1 for chlorine. Here's bromine's 79 and bromine 81 in a 50.7 to 49.3. So roughly 1-to-1, 79 and 81, the mass comes out right in between on the periodic table. Okay, so this is 3-to-1 and bromine is 1-to-1, right? And carbon has this 1.1%, which we said was the M+1 peak. Okay. All right, so there's two things here. The chlorine and bromine, especially, we can just pick out by the ratios of the peaks. And the second thing is, if we want to add up the masses, then we have to, usually we just pick one of these, the most abundant mass, as even whole integers, and we add those up. Okay? Other thing that we can use that information for is if we have a mass spectrometer that can measure the mass out beyond the integer level, out 3 or 4 or 5 decimal places, we can actually tell the difference between different molecular formulas. Because, like we saw on the last slide, the masses of those isotopes that are in there don't all come out to just an even mass. Only it's 12.000, but all the other ones are a little bit off. Okay? So, for example, let's look at this mass of 108.057. So let's first come up with a formula for 108. Okay, and we'll follow the procedure that we did last time. So we start out with 108, and what did we do first? We divide by 12. And if we do that, that gives us, comes right out to 9. Okay, so this would give us a starting point of just C9. C9. All right, but we should have some hydrogens in there. So the first thing we're going to do is take off one of those carbons and add 12 hydrogens. We're just going to trade them in. Right? It's not a chemical reaction or anything. We're just accounting for coming up with possible formulas. So we're going to minus a carbon. We're going to add 12 hydrogens. So we get to C8H12. All right? Does that seem like a reasonable formula? Could it be a possible formula? Yeah, it could be. So let's keep going, and come up with some other possible formulas. All right? If we did the same thing again, would that be good? If we added 12 more hydrogens on? No, that would have too many hydrogens. So what we can do is consider adding oxygen. Right? And when we did that, remember, to add an oxygen, we subtracted a CH4 and we added an oxygen. So we're just trading in atoms. So if we did that, we should get C7H8O. All right? Let's do it one more time just for the fun of it. Okay, so we're going to minus CH4. And we're going to add an oxygen, C6H4O2. Okay? So let's just imagine these formulas, all right? And what I did is I went up and I took all those accurate masses and I added them up for each of these formulas. Or actually, I just looked at the table. Okay, so if we add those up for CH8H12, C8H12, it comes out to 108.0939. Okay, the 108 fits great. Okay, If we do the next one, C7H8O, C7H8O, we add all that up, 108.0575. Okay, if we added them up for C6H4O, it adds up to 108.0211. All right? So all of these formulas add up, if we were just adding them up to unit numbers, they all add up to 108. Okay? But if we use the information on that last slide and we know that, for example, the proton is 1.0078, right? And oxygen, I did have that on the oxygen is like 15.99 something. So they're a little bit off from the even numbers. They add up differently. And so from this, which one of those formulas looks like the right one? It's the middle one, right? Because that matches this. Okay, so we could do this experimentally. So if you wanted to know the formula, what you might do, you probably have to pay a little bit more for somebody to run a high-resolution mass spectrum. But you can do that, measuring it out to, say, 4 decimal places. And then as the molecule gets bigger and bigger, you may not always be able to just pick out a single one, but you can at least narrow it down. Yeah, question?
So if you're using a halogen, chlorine, or bromine, how do we do this with those?
You could do the same thing with a halogen.
Just do it with both isotopes separately.
Right, they'd measure the isotopes independently. Okay, and each of those isotopes has an accurate mass as well.
Because your calculations are based on the primary isotope.
Right, usually you use the most abundant isotope. Yeah. Anything? Okay. Yeah, question?
So in plants, they have a different C12 to C13 ratio.
Right.
Throw this off, trying to find the molecular formula.
Okay, so the question was in plants, because in plants they have a slightly different ratio of, say, carbon-12 to carbon-13. And in fact, this can be used for, to follow biosynthetic pathways and to measure carbon dating and this kind of thing. That doesn't matter, because it doesn't matter, we're not measuring a ratio of those isotopes, we're looking at one ion that has a certain combination of isotopes, right? So the carbon-12 from a plant versus an animal is going to have the same mass, even though its ratio of carbon-12 to carbon-13 is different. Okay? Yeah, question?
So usually you'd have to run this mass spec several times to get an average. Get like a random one with C13 instead of C12 sample.
No, what you'd actually do is you just run the spectrum and you would measure the mass of those individual ions. And so you can measure the mass of different ions in the spectrum all at once. Well, sometimes what they do is they don't actually, to do it very accurately, they sometimes use a standard, a molecule that they know if you have an unknown, that has a mass very close to the one that you want to analyze. And then they compare the masses and they can do it very carefully in that way. Okay? All right, so this is like the ultimate way in mass spectrometry to get the formula. But we want to always have this data. You guys didn't pay enough on your tuition to have this kind of data every time. Yeah?
How long have we known about this? How long have we been using it?
Oh, probably since the 50s or 60s or something like that. Maybe before that. All right, so we've come up with a molecular formula. What can we get from that? Okay, one useful piece of information is just to calculate what we call the number of unsaturations. All right, so what's an unsaturation?
Double bond.
Right, it's essentially a loss of 2 hydrogens, which can be accounted for either by a double bond, a pi bond, or what else? A ring. right? So if we're trying to figure out what the structure is, it's helpful to know right off the bat from the formula whether there might be any rings or double bonds in it, right? That's just some information that we get. So there's two ways that I'm going to show you to do this, okay? The way that the text does is they just take this formula, they look at the number of carbons, and from that carbons they consider or they calculate what the maximum number of hydrogens would be. What's the formula for the saturated hydrocarbon? Okay, so they'd say C8, and how do we calculate the maximum number? 2n plus 2, right? 2 times 8 is 16, plus 2 is 18. Okay, and then what they do is they just compare this 18 to 12. Okay, so 18 minus 12 equals 6. And for an unsaturation, every unsaturation is the loss of 2 hydrogens. So we would just divide that by 2. 6 divided by 2 means that we have 3 unsaturations. Okay, so this molecule, a molecule with C8H12, could have 3 rings. It could have 3 double bonds. It could have a ring and a triple bond. It could have, a triple bond and a double bond. All those would be ways. 2 rings and a double bond. Those are all ways to come up with 3 unsaturations, right? So it didn't solve everything, but it narrows things down or gives them some information. Okay, I'm going to show you now, though, another way that you can do this. This isn't in the book, but you can use this if you want. And this is just a formula to calculate this out instead of going through this kind of stepwise fashion. Okay, so this is my formula. I didn't invent it, though, but I've used it a lot. What you do is you take the number of carbons, you subtract from that half the number of hydrogens. All right, if there's nitrogen, you add half the number of nitrogens, and then you add 1. Okay, so let's try it for that formula up on top.
Is that a number 6 there?
Oh, right. Yes, why was I thinking of that? That is the number of carbons, not a 6, not always a 6. This is the number of carbon atoms. All right, so let's try it up here. So the unsaturations equals, here we have 8. We subtract 12 divided by 2. There are no nitrogens, right? We could write it here, plus 0 divided by 2, plus 1. Okay, so 8 divided by 6 is 2, plus 1 equals 3. Okay? So for the next one, we have a bromine. So in either approach here, we're going to just count a bromine like it was a hydrogen. Okay, because it has all the same bonding. It just has a 1 bond. Okay, so let's do the same thing we did before. So here we treat like hydrogen. So we're going to say unsaturations equals, we have 5 carbons, minus, we're going to have 9 hydrogens plus a bromine, so we'll just say minus 10 divided by 2, no nitrogens, plus 1. Okay, so 5 minus 5 plus 1, this has 1 unsaturation. So we could come up with, this could maybe be, let's say, bromocyclopentane, right? We'd have 1 side of unsaturation. Or it could be, we could just put a bromine on here. Bromopentene. Okay, those would all fit that. All right, so what about the bottom one? This has a nitrogen on it. If you're going to use the way that they show in the book, you subtract a hydrogen instead of adding a hydrogen for a halogen. But you can just do this with this formula. Unsaturations equals the number of carbons is 7 minus 5/2 plus, now we have 1 nitrogen, 1/2 plus 1. Okay, so it's 7 minus 2.5 gives us 4.5, plus 1/2 is 5, plus 1 equals 6. All right? So the structure I was thinking about when I came up with this, 6 is a lot of unsaturations, right? But if we had, say, a benzene ring, how many unsaturations are in a benzene ring? 4, right? Because there's 3 double bonds and there's a ring. Plus, what do we have left over? Let's think about this. This is 6. If we have one group attached, C6H5, what do we have left over? This is C6H5. Compare that to our molecular formula. And what's missing? A carbon and a nitrogen. So what? Right. Or yeah, we'd call it. Cyanide is usually Cn minus by itself. If we attach it to an organic molecule like this, we usually call this a nitrile. Okay, so we have a triple bond, that's 2 unsaturations. We have 4 from the benzene ring, gives us 6. Okay, so this plus this. All right, so this formula, you can get the unsaturations for any molecule like that, okay? All right, any questions? Okay, so let's look at fragmentation, or, well, we're not going to really look at mechanisms here. We're just going to look at some common cleavages, okay? One that I'm going to call a sigma cleavage just means that it's cleaving a sigma bond. And the most common place, really the only place that we see this sigma cleavage is for alkanes. All right, because it's quite high energy to ionize and cleave a carbon-carbon sigma bond. And if we have some other functional group where we have either non-bonding electrons or pi bonds, those are going to trigger the cleavage. Okay? So this kind of sigma cleavage is kind of what we talked about yesterday. Let's say that we're starting with just propane, just so we don't have to draw a lot of things here. We're going to ionize this, and really the only electrons that can be lost are either in the carbon-carbon bonds or the carbon-hydrogen bonds, right? So I'm just going to draw this like this. See, I'll draw these hydrogens out now. And what I'm going to draw is the bond like that. So a full bond would have 2 electrons, but we've knocked that one out. Okay, so this is our, so we've lost an electron. This is our molecular ion, and it's a radical cation. So now just imagine that bond, because it only has 1 electron in it, is very much weakened. And so that bond can break. And it can break in 2 different ways. Okay, it can fragment to give us the plus on this side plus the radical on this side. Okay, so the electron goes to one side, leaving the plus behind. Or it can cleave the other way, giving the radical on this side plus the methyl cation on the other side. Okay? So, if it had these 2 possibilities, do you think that one of those cations would be more abundant than the other? Is one more stable than the other? right? Because what do we have? We have a methyl cation versus a primary carbocation. Which one is more stable? Primary is more stable than the methyl, right? Methyl cation is the most unstable, right? So this one right here should be the most prominent of these two possibilities. Okay, the other possibilities, we could break a carbon-hydrogen bond, which in fact we could then get a secondary carbocation as well. Okay, in each of those cases, this would be called a sigma cleavage, though, because we're cleaving a sigma bond. All right? But these only really take place when we have alkanes. If we have other functional group, then there's a more facile cleavage pathway. Okay? So this alpha cleavage makes more sense if we actually drew out all the mechanism, but here let's show first one of the examples that they showed is if we have a carbonyl compound like this, right? I'm going to put an R and I'm going to put an R prime, just meaning that those two groups could be different from one another, right? They could be a methyl, an ethyl, or a hydrogen or something like that. The way that this alpha cleavage goes is it cleaves the bond adjacent to the functional group. And the charge is going to go to the side where the carbonyl group is. All right, that's why I'm going to draw that arrow going that way. That's the side that the charge goes. All right, so if that happened, we could get a species that looks like this. So we have two non-bonding electrons up here. This, in fact, has a resonance structure that we could draw, that's commonly drawn, where a pair of these electrons come down here, are donated to the plus. And this gives us a triple bond to the oxygen. And this whole species here is called an acylium ion. All right, and then what would be the other species we get? We get a cation plus a radical. So whatever this R prime over there was, that would be the radical. Okay, if it was a methyl group, we'd lose 15 and we'd get the acylium ion. Okay, if there was an ethyl group on the other side, we could lose that ethyl group as well and lose 29. Right? So in that way, sometimes we can, if we had a ketone in an alkane, we could tell where the carbonyl is because two pieces are lost, one on each side.
And that's just because it's more stable?
Because the acylium ion is more stable? Well, I think it's because there's just a lot of energy in there, and it's just kind of blasts it apart. And this is one way that it can cleave. Yeah, question?
Why would you call it alpha cleavage if you're breaking the sigma bond?
Right. The alpha comes from the fact that I think that it's always cleaving on the adjacent to the cleavage. Because the way that this actually works, no, I'm not going to even go in there. Usually, in the last text we had, we actually drew all the arrows and everything for these. But this one doesn't do that. It's just on the other, it's just right next to the functional group, I guess. It's actually one carbon past where it ionized. Usually what would happen on a carbonyl like this, the easiest place to ionize is on the non-bonding electrons. Okay, so we could show the molecular ion like this. And then the way it would cleave is this radical would donate, we haven't done radical chemistry either, would donate it down there, combined with that electron, and cleave this bond like that. So the carbon bond would split with one electron going to each side. And that would give us the cation on one side, and this other piece right here would come off with a radical. Okay, the same kind of alpha cleavage can happen with alcohols as well. this is just, I'm going to put the hydrogen here. So again, this can cleave like this. Okay, and if it did that, you could get this cation here, which has a resonance structure as well. Like this, plus a radical, okay? Or, you know, it could cleave the other side as well, okay? Just like with the ketone. So if it did that, it would give R radical plus the same kind of species on the other side. This is the R prime, the plus, okay? So we can lose one side or the other side. Okay, so these are common, two common cleavage mechanisms. Okay, sigma if we have alkanes, or this alpha cleavage if it has a functional group like this. All right, so let's look at examples. Okay, so both of these spectra are from alkanes that have the same formula. All right, so here's the molecular ion is at 100. Okay, you can barely see it, but there's another molecular ion for this one right here that's also at 100. Okay, so these two compounds are constitutional isomers of one another. Okay, notice that they both have the same base peak, is at 43. But the one at the top has several more major ions, right? So this has at 85, this is at 71, this one is at 57. And in fact, this is the spectrum. No, we didn't see this one. So this one, remember, so what we see is 15. And then the differences here, this isn't the way it fragments, but what's the difference between each of these? 14, right? 14 to 14 to 14. And these are all pretty good size ions, and so it turns out that this one comes from just heptane. Okay, the bottom one, notice that we don't even really have the ion at 71. Okay, we have a bigger ion at 85. Okay, what was 85 generated from? What did we lose? A methyl group, right? So this is loss of methyl. There is some at 57, but there's a big one at 43. Okay? So what this means, because we're not getting all those ions, what it means is it's the alkane is probably branched, and so we have one or some ions that are more stable than others. Okay? And so this spectrum comes from, it's just from 2-methylhexane. Okay? So the big ion at 43 comes from cleavage right here, right? And the ion is going on this side. So that would be this secondary carbocation, okay, plus this radical. Okay, so this is 43. Okay, what about the 85? Where would we lose the methyl group? Right, we have 3 methyl groups, right? We could lose either this one over here, or we could lose either one of these two. So do you think you're going to lose this one preferentially? If we lost this, cleaved here, what kind of a carbocation would we get? Primary, right? If we cleaved, say, this one here, what kind of carbocation would we get? secondary, right? So we're actually more apt to cleave this one with the charge going that way, right? And so this gives us this carbocation, which is at 85, plus the methyl radical. Okay, so we're seeing more of these ones that are big. I think what happens is one at 57, if we cleave the bond, let's see, where's my... If we cleave the bond right here, and we take the other piece, that ends up being 57. Okay, so if we ionize next to the double bond, but the plus goes to the less substituted side, and so that's why the 57 is smaller. Okay, so we still kind of see things, some things that are 14 apart, but we don't just see kind of equal amounts or this kind of increasing amount like this. We have certain ions that are much more prominent than others. Dang, we're out of time. I'm just getting going and having fun. Okay, so why don't you, if you guys have these, why don't you take a look at these and see this one and the next one, if you can figure out for these two isotopes, each case, this one is for alcohols, the next one is for ketones, see if you can come up, or one, the carbonyls aren't just both ketones, see if you can figure it out, and we'll look at it tomorrow. Yeah, exactly.